Okay, we're live when you want.
Okay, so welcome everybody. Today we will listen from Tomás Müller, that is a Juan de la Sierra fellow here. He studied in the University of Southampton, his PhD, and now he has been here as a postdoc and now as a Juan de la Sierra. So he will tell us something about the effect of host-galaxy environment on type 1a supernova standardization. Please, Tomás.
Okay. Thank you, Daniele. So first of all, thank everyone for being here today. And yeah, so this is another supernova talk, but don't worry, I'm going to talk about something slightly different than what Krista talked about. So this is a project that I've been working on with the student here, an undergrad student. Yeah, so the outline of the talk is I'll start just briefly discussing what type 1a supernovae are, what they look like. Then I will go on to how we do cosmology with type 1a supernovae. After that, I'll talk a little bit about the host galaxy properties. Hotspot, which is a package that I have developed here with the help of Dries. And I will end up talking about the effect that the environment has on type 1a supernovae and what in the case of cosmology. And yeah, this is a nice picture I'd like to start with. This is a supernova 2011 FE, and it's one of the most nearby supernova that we have, type 1a supernova that we have. And yeah, the galaxy is just great, and you can clearly see the supernova there. And this is a very beautiful picture. Okay, so just a reminder, of course, Krista already described this, but it's good to remember how we classify type 1a supernovae, different types that we have. So we have a new transient in the sky, so something that was not there the night before. And now we find this new thing, and we take a spectrum, and we look into the spectral lines, and depending on the different lines, we classify them, right? So if the supernova has hydrogen, then that's a type 2 supernova. It's quite simple. It's what we see down here. In red are the hydrogen lines, or H alpha, H beta, for example. Then if there's no hydrogen, but we have helium, that's a type 1b. Although I'm lying a little bit because it's not a strict definition. Some 1b might have a bit of hydrogen, but in general, they mainly have helium here, what we see in yellow. And then if there's no hydrogen and no helium, that's type 1c, which is the third one from bottom to top. Now, these are all known as core collapse supernovae. This is let's say a classification according to the physics of their explosion. So they come from massive stars when the core collapses and produces the supernovae. And then if we have no hydrogen, but strong silicon lines, like we see here, the top spectrum, green, then that's a type 1a supernova, and that comes from a thermonuclear explosion. And for doing cosmology, we mainly work with type 1a, although you can also do cosmology with, for example, type 2 supernova, but I will not talk about that in this talk. Okay, so how do we actually classify them in practice? So, okay, we take the spectrum, but do we actually just see the lines? Well, the truth is a bit more complicated. So we don't actually just look at the lines. Sometimes we have some peculiar types. So there are lots of subtypes of supernovae that are hard to identify. But in general, it's what we do. So there are some other options, but one option is to use compare it with the templates, right? So we have the spectra of other supernovae that we have classified before. So we compare with templates. There's the case, for example, of gelato that we use in the PESTA collaboration. So we classify supernovae and we also do follow-up. But for the classification, we just take, for example, in black is the new transient, the unknown transient, and in blue is just a comparison spectrum. And in this case, this is type 1b supernova. So we see that they look very similar. Okay, yeah, they look almost identical. So then we classify this as a type 1b. There are other similar tools out there like SNe, and it's essentially the same. In this case, SNe also gives you a rough estimate of the redshift as well. So in this case, this is a type 1a, normal type 1a supernova, and we can clearly identify the silicon lines here and here. So yeah, as you can see, it's well, it's not a very sophisticated method, but it works. There are some machine learning tools as well, some more fancy tools, but this works as well. And we're not classifying like hundreds or at least thousands of targets per day yet. So this works for now. Yeah, now into type 1a supernovae. So yeah, again, Krista already gave a wonderful description of what they are, so I will not go much into the details. So yeah, they come from the white dwarf in a binary system, and they are very bright explosions, and they are relatively homogeneous. And here we have a nice data set from, yeah, I didn't put the name of the supernova, I forgot, but we have all the way from the UV down to optical and near infrared. And most of the light come from the optical, let's say, part of the spectrum. And you can see that as we go into the near infrared, it starts developing a secondary peak. But for the sake of this talk, I'll just focus on the optical light. And well, if you have any question, like in between, you can just ask me.
Very quick. So
Yeah.
the secondary peak is a common feature in the infrared?
Yeah, we see this in all type 1a supernovae. This is common. And yeah, so again, not talking about the near infrared, but we also use them in the near infrared, which is what we are doing with GIS to do cosmology. But yeah, we can talk about that later if you want. Okay, so yeah, let's start talking about cosmology. So this is talk about cosmology, not much about not really about the physics of supernovae. So yeah, type 1a supernovae, they are known as standardizable candles in the optical. It means that we can get a bunch of optical light curves. We can correct them so they all look very similar, especially at peak. And where do these corrections come from? So we see that the peak brightness correlates with different parameters. So for example, we have the stretch. The stretch is just the width of the light curve. So like brighter supernovae, they rise and decline more slowly, for example, and vice versa. Also, the peak brightness correlates with color and even with the host galaxy properties. And I'll go back to this third point here in the talk. So essentially, to measure distances, the distance modulus is equal to the apparent magnitude, the peak apparent magnitude in the optical. You apply these corrections, and then you subtract the absolute magnitude. Of course, for this case, we need to know the absolute magnitude of type 1a supernovae. And again, I'll go back to this in a second. So yeah, in principle, it's really simple to measure distance. And just to go a little bit more the details here about the stretch parameter. So this was first introduced by Phillips, only like almost 3 decades ago. The still 15 parameter that he used is just the difference in magnitude between the peak and 15 days later. So if we plot this versus peak brightness, we see that like normal type 1a supernovae, they follow this nice relation here, Phillips relation. And we have some other peculiar type 1a supernovae that we don't care for cosmology. Anything that doesn't follow this relation it's weird, it has like weird colors or stretch. We remove them and we don't care about those. We just care about the normal type 1a supernovae for doing cosmology. Now, to obtain these parameters like such as color and stretch, we get them from the light group, right? But usually you don't have a complete light group. You don't have a nice data set as the one that I show here. Right? This is very rare. This is mainly for nearby supernovae. Even for nearby, you don't have these nice data sets. You have like large gaps in the data. So for that, we use light group filters to have a continuous light group and to extract light group parameters. There are a few out there. These are not all. There are a few more. So there's, for example, Snoopy here that was developed by Chris Byrne. Piscola was developed by me during my PhD, very Chilean name, as you can guess. And we have also Salt 2. Well, there's also Salt 3 nowadays, was developed by Gui, a French guy. I don't know how to pronounce the surname. But yeah, there are a few options, right? What? D. Thanks, Luis. Yeah. So yeah, there are some similarities and some differences between these different light group parameters. So for example, Snoopy and Salt 2, they are trained on data sets. They have an SED model of type 1a supernova that they train on well-observed supernovae, right? So these are usually low redshift supernovae because we can track the whole evolution in different wavelengths, and they have an SED model that they train on this data. In this case of Piscola, No, this is a data-driven light curve fitter. It uses Gaussian process to fit the light curve, so it is model agnostic in that sense. And you can even use Piscola to fit other types of supernovae, right, or the transients or anything, because it doesn't have an underlying model of the light curve. So of course, there are some advantages and disadvantages in the case of Piscola. The advantage is that because it is model agnostic, you can find some interesting features. You can extract a nice thing that you might miss with this template, right? But the good thing about template is that even if you have few data points, you can fit a light curve. In the case of Piscola, if you don't have, let's say, like a good amount of data points along the light curve, or you don't have small enough error bars, then the fit's not going to be very good. And I'll go back to Piscola later in my talk. Okay, now going back to measuring distances with Taiwanese supernovae. Now we're going a bit more into the details here. So this is what we want, the distance on this side. We have all these other parameters on the other side. So in green, these are light curve parameters. So what we measure. So we have the optical peak, in the V-band in this case. In the optical, we have stretch. So these are SAL2 light curve parameters. And I'm talking about SAL2 because this is the one that most people use nowadays. We have color, and this is host galaxy properties. It has nothing to do with the light curve in principle. But I'll talk a little bit more about that later. And the rest, these are just nuisance parameters so free parameters that we fit later, right? So to build our Hubble diagram, well, we see here on the right, again, we need to fit the light curve, get the light curve parameters, and we need to minimize this residual up here, right? So on one side, we have the distance from the supernova, right? The luminosity distance, and then we have the distance according to theory. So you can take your favorite cosmology, let's say lambda CDM, and your cosmology has some pre-parameters. For example, you can have omega matter, omega lambda, W, which is let's say the evolution of that energy. And yeah, you want to minimize these residuals, so you fit the free parameters on both sides. On the supernova side, which would be this nuisance parameter here. And on the theory side, your cosmology, your omega matter, omega lambda, and so on. And this is what you get, right? So you get your nice looking Hubble diagram. And you can create some nice contour plots. So in this case, we have omega matter down here, omega lambda, and yeah, you get your estimate of the cosmological parameters. And in this case, I'm showing the results from the Pantheon Plus sample. So this is the largest sample to date of Taiwanese supernovae. So we have over 1,500 Taiwanese supernovae. And you can see here the description of the sample. So this is just showing. So this work has been building upon previous works. So we have Pantheon Plus, we have 800 supernovae from last year. We have the Pantheon sample, which had roughly 1,000 supernovae. This is from 2018, and JLA was before that 700 supernovae in 2014. Right. And yeah, down here you can see that the Pantheon sample is actually a compilation of different surveys. So you have supernovae from observed from different surveys, all the way from low redshift like CSP and a few others, and going to high redshift, for example, with the Hubble Space Telescope. So there's a lot of work going on here, a lot of effort. Especially because you have like so many different surveys, you have different magnitude systems, there's so many things that you need to correct for, and so many things that can go wrong. But the people working on this are very smart, so they're doing everything. They're doing a nice job here. Yeah, so I talked about cosmological parameters, H naught, omega matter, omega lambda, and such, but I didn't talk about H naught. Right. So how do we get H naught? Well, I didn't mention it before because, well, if you want to get, for example, omega matter and omega lambda, you don't really need the H naught. So H naught in this Hubble diagram is just scaling in the y-axis. And omega, as you can see here, omega matter and omega lambda, they just they have to do with the shape of this Hubble diagram, right? They affect a larger redshift. So they don't really care about what happens here at the redshift 0. But then how do we get H naught with supernovae? So in here, I'm just explaining what the SHOES project collaboration is doing. And yeah, So in principle, we only have supernovae. They are really far away at high redshift, and we need to calibrate their absolute magnitude. Before I told you that we need the absolute magnitude of type 1a supernovae, but how do we know the absolute magnitude? We need the distance, right? So this looks sort of like circular. So yeah, we need to calibrate them somehow. Right. If we look into our local neighborhood, now we can measure distances using parallaxes, for example. So we can get distances to stars here in the Milky Way. We can get the distance to the LMC M31. That's great, right? But still, this is very local. We cannot reach type 1a supernovae that really far. How do we connect these 2 points here? Yeah, for that we use Cepheids. So how does this work? Cepheids are variable stars. They follow this period luminosity relation that we can use to estimate distances. But we also need to calibrate this period luminosity relation. And for that, we measure first the distances to Cepheids in the Milky Way, for example, or in the LMC. And with that, we calibrate the period luminosity relation of the variable stars, these Cepheids. And then we look for Cepheids in other galaxies farther away, right? So Cepheids are also bright stars, so we can look a bit farther. And if it happens that we have a type 1a supernova blowing up in one of these galaxies as well, then we can use these Cepheids to calibrate these type 1a supernovae, which are here in red. Right, so now you have this whole three-step ladder to get all the way to calibrating type 1a supernovae. And with these red ones here, you can calibrate the rest. And because you're calibrating your absolute magnitude here, you're also calibrating in the whole diagram your y axis offset, and you get your estimate of the H naught. But yeah, of course, it depends on the calibration of these two guys here. Now, when we measure H naught using type 1a supernovae, we get a number, and it is roughly 73, right? That's great. We have relatively small uncertainties here, but we can also measure H naught from using other probes. If we go to the early universe, we can use CMB, right? And what they do is, they do their measurements of the CMB, and they assume a cosmology, in this case lambda CDM, and they extrapolate from the early universe to today, and they get their measurement of H naught, and this is what they are showing here, and we have a tension. So it's more than 3 sigma difference between both measurements from the early and late universe. It's actually closer to 5 with the Schu's measurement here compared to Planck. And this is really weird, right? So why? No, they should be the same, right? They should match. They should be in agreement. So why are we having different measurements here? This is a question that we are still dealing with, and we have 3 possibilities, right? So the first possibility is that we have a bias from the CMB measurements in the early universe. So these guys are messing up, right? You guys are not doing your job correctly. That's one option, right? The second option would be we have some systematics on the late universe measurements. So we supernova people are doing something wrong with our measurements. Or the third option is like, no, we're good. Theory people are messing up, right? So people working in theory, your lambda CDM model is not good because it's breaking here, right? So you should change your lambda CDM model, should modify or create some alternative models. Now, I trust that the theory people, they're very smart. I've been to a few talks, conferences, and there are lots of models, and they do not seem to solve this issue, right? So they try to solve the tension, and if they do solve the tension, they break somewhere else. So at least so far, they haven't found an alternative model that is better than lambda CDM. So, okay, let's say that, okay, you guys are good. Let's say we trust you. Then let's look into one of these 2 things, right? Of course, I'm not a CMB person. I'm a bit open to discussing things. So, okay, let's see if we can find some biases on the supernova side. And that's what we are doing, right? With this project with the student. And I'm more specifically looking into the effect of the environment the host galaxy has on type 1a supernovae. In the distance we measure. So yeah, going to galaxy properties, we know we have different properties for the galaxies. We can we have the age, metallicity, stellar mass, star formation rate, and so on. We have lots of properties. And how do we get these properties? So, well, I'm not an expert on galaxy, but essentially we get this from the spectra, right? So we have a spectra covering a wide range of wavelengths. We can see that different components contribute in the different parts. We have young stellar populations. We have older stellar populations, the bulge. We have dust, and so on, right? So there's a lot of things going on, and we can sort of like from here get to these parameters. And yeah, of course, there's a lot of theory behind this. So we have things like different things affect into the the properties and the spectrum that we see. We have, for example, the initial mass function, the isochrone, so the evolution of the stars, stellar spectra, the chemical evolution of the galaxy, and so on. So all these things contribute to essentially the spectrum that we measure, and then we can fit. So we have different galaxy SCD filters, and we fit different parameters, and we get our properties, right? Of course, it would be great if we could have a spectrum for every single galaxy, but in reality, that's not possible. It's really hard to do. So usually we deal with photometry of galaxy, right? So we take photometry, UV, near infrared, optical, and then we fit that, which is what I'm showing here, right? So these sort of like black dots here are the photometry, and then we fit the SCD model. But it works. Okay, so we have the parameters that is what we want. Okay, now people have wondered about this. Supernova people have wondered about this for a long time, and it was actually like over a decade ago that we realized that the galaxy, or the environment in which supernova explodes, it does affect the brightness. And then here, and just showing one example, they show that we have the stellar mass of the galaxy down here, and this is essentially the brightness of the supernovae after correction. And what we see here is that brighter supernovae, they tend to be in more massive galaxies, and vice versa. So of course there's something going on here, and we need to take this into consideration for measuring distances. That's why at the beginning I told you, okay, we correct for Likert parameters, but we also correct for host galaxy properties. So we need to take this into account in order to avoid biases, and also to reduce the scatter and Hubble residual. Right, but now this is the stellar mass of the whole galaxy. But we know that supernovae, they explode in tiny little regions in galaxies. So is let's say the properties of the whole galaxy, is it representative of the neighborhood where the supernova explodes? That's a good question, and people have worked on this as well. So we have this image, for example, and we see that, okay, so we have the whole galaxy. But in this case, the supernova exploded in the center of this, we have this aperture. So if we measure the photometry there and fit our SCD model for the galaxy, we get some different values, right? And well, maybe it's not so clear from here, but we see that this correlation between host galaxy properties and the brightness of supernovae is tighter if we use local properties, right? And this makes sense because the global properties are not going to be as close as the local properties of where the environment with the supernova explode. So, well, that's good. It means that we can improve our corrections. And it has also been done not only with the stellar mass, but with different galaxy properties, such as color, for example. We have here the specific star formation rate, and we always see this trend, right? So people are still like looking into the details, although let's say the exact mechanism or thing that is driving this correlation is still unknown. It's probably a mixture of, so all these parameters are correlated, right? So they're not independent. So probably the true underlying reason behind this correlation is something that involves all of these, but still like unknown, and we're still looking into these. Okay, now going back to global and local properties, there are some issues here. So if we look into this plot here, so we have the global stellar mass of the galaxy and local in the neighborhood of the supernova. And of course, in the case of stellar mass, we see some offset. And this is expected because if you add the flux inside this aperture, it's going to be less than of the whole galaxy. And makes sense. But we also see a large scatter, right? So, well, this in principle can depend only on the position of the supernova. So if the supernova is really far away in the outskirts, then the mass that we measure is going to be much lower. But if it's closer to the center, it's going to be larger. But there could also be like other things driving this scatter. And one big issue here is that as we go to higher redshift, we start probably like missing some flux. And why is this? Right? If we have a nearby supernova, we can clearly see the outskirt here. But as you go, a nearby galaxy, we can clearly see the outskirt of the galaxy. But as we go to higher redshift, then this diffuse part it's just within the background noise. So then we're not measuring these flags. So we're probably just measuring like lower limits in this case, right? So this is a problem. And again, we're still working on this. It's not easy to solve. Now going back to the, let's say to the project that we are working on. I actually talk about the hotspot first. So how people, you get the photometry in order to get your host galaxy parameters, but every project, every analysis does it in a different way. So because of that, it was hard to replicate different works. So that's why we came up with hotspot, which is a code for downloading images and getting photometry of galaxies, right? In this way, this is all publicly available. It's open source, so people can use this tool. And we are all happy that we measure the photometry in the same way. Yeah. So far we have implemented a few surveys, as you can see. So the UV have Galax, SPSS, DES, Pan-STARRS legacy survey in the optical, a few in the near infrared. We have TUMAS, LISTA, WISE, and Spitzer in the mid infrared. Of course, not all these surveys take up the same part of the sky. But yeah, there's more surveys can also be added also in the future, or if you have other suggestions. There's a lot of documentation here about hotspot in the GitHub repo and everything. So you can look into it if you're interested. Or even if you just want to download images of parts of the sky, you can use it for that as well. Yeah, so as I said before, the first step is to download images. So now you put the coordinates of the galaxy, you center it there, and you give the size that you want. And we see the nice looking supernova closer to the center of the galaxy. And then we can do some masking, right? So there are some foreground stars here that I will add to the flux of the supernova, the galaxy, if we don't remove them. So hotspot can also identify targets here and remove those. So then we have a clean image. And then comes the next part, which would be to get the photometry, right? So then we take our aperture and we get the global photometry of the galaxy. You do this for as many bands as you want, or they are available. You can also do it for local photometry. Yeah, so local photometry, you center it, for example, where the supernova is in this case, and you give the size of the aperture, in this case, 4 kiloparsecs. But you might want smaller, larger, it's up to you. Of course, in this step here, I'm assuming extremely to have a physical the radius of the aperture. But we essentially want to use the same aperture for all supernovae, because otherwise we will not be tracking the same neighborhood around the supernova explode. So of course this changes as a function of redshift. And then you use your favorite galaxy ACD filter to obtain your properties and do whatever you want. So yeah, like going back to this question, so we know that the environment affects type 1a supernovae, but does it affect them in maybe some ways that we don't actually know? So there may be some hidden biases. So this is related to the Hubble tension. We're looking for biases here. So I'll talk a bit about the color law. So maybe say something a bit odd, but the color law is essentially, as I wrote here, is how the color changes as function of wavelength for type 1a supernova. And well, this is actually what we see here is actually the color, right? So this is a plot waveline, roughly just optical. And here we have A sub lambda minus A sub B. So you can think of this as color, and we're taking the B band as reference. So if you go like here, you have U minus B, or if you are here, you have B minus B, for example. But this is, okay, so this is the color law, and this is just a polynomial. And in the case of SALT2, so SALT2 describes, as I said before, describes the SED of a Taiwanese supernova using a model, right? And this model is here, it's described here. So the flux of the SED is just a global scaling of the pole CD, x of 0. And then you have here M0. So M0 would be the average SED of a Taiwanese supernova. So you can think of that as like this solid red line that you see here. So that's M0. And then you have a little bit of variability, depending on, in this case, the stretch of the supernova, so the width of the light curve, multiplied by this M1 that is just like variability. And for example, with that, you can get, for instance, this dashed red line there. And you also add the color of the supernovas. In the exponent here, you have C, small c, which is the color, and CL, which is the color. And in the case of SALT2, so SALT2 assumes that all supernovae, they have the exact same color, right? Which is, okay, they're assuming that this is the model that they came with. And they trained this on well-observed Taiwanese supernovae before fitting other supernovae. But no, there might be some issues with this. So now the question that we raise is that, is the color law actually unique for all supernovae, or no, maybe it has some environment dependency, right? Maybe we shouldn't use the same color law for all supernovae. So maybe the model could have some bias. So we can test this with Piscola. And why Piscola? Because again, this is a data-driven light curve fitter, so it is model agnostic. So we can estimate the color law directly from the data. So we are letting the data tell us the color law looks like this, instead of just imposing the model. Yeah, we do that. So we take the dark energy survey 3-year sample, and we fit. So we extract the color law for different colors, and we fit a polynomial. Right. So with the same polynomial that SALT2 uses, we fit a polynomial here, and then what we do is compare the color law that we get versus the one that from SALT2. And here we're using all the supernovae, where we're not making any distinction here. And what we get here is in black. So in black we have the color law from Piscola, and in blue that's the one from SALT2. In red, these are just dust extension laws for comparison. And although there's some slight disagreement on the edges, overall they agree, and well, they do agree within the uncertainty. So what we find here is that, okay, we retrieve from the data the color law from SALT2. So in principle, okay, the color law is good, it's working. We directly from the data we get this color law, which is fine. We sort of expected that. But now we want to see if if we split the sample into different, for example, supernovae exploding in high mass galaxies and those exploding in low mass, we get different results. And this here I'm showing the host galaxy stellar mass, so global versus local, and we see something interesting here. So this is all preliminary work. We're doing the whole analysis with much more detail. So things might change a little bit here, but we see that, okay, in blue these are all low redshift supernovae, in red are higher redshift supernovae, and we see that the low redshift supernovae, they tend to have larger mass, so they are in more massive galaxies. And is this a observational bias, or are actually host galaxies in the local universe that they're more massive? So this is really interesting here. No, we need to analyze this and see this. Let's see what we see here makes sense, or why do we get this difference, for example, between the low redshift and the high redshift supernovae. So that's we need to do that. We need to analyze that as for the future. And this is essentially the results of the comparison. So up here we have the color law from supernovae exploding in low mass galaxies, and here supernovae exploding in high mass galaxies. and well, we essentially see no difference. So this is, of course, not as exciting if we would have seen some difference, which means that, okay, there's some host galaxy environment dependence on the color law, but okay, this is still good. It means that the SALT2 model is reliable, as that the color law actually it is sort of unique for all supernovae. And it means that at least from this part, there's no bias in the SALT2 model, right? So the environment does not affect the color law. So let's check for the SALT2 model. And it means that we're doing things right with that likelihood figure. So yeah, that's sort of the end of the talk. Yeah, just to summarize, the Taiwanese supernovae, they're excellent cosmological probe for measuring different measurements, for having different measurements, but for that we of course we need to standardize them, and we can even use host galaxy properties to further standardize them. So use that as a third parameter for correcting the light curves. We have an H-0 tension between early universe and late universe measurements, and no, we can. As the theory cannot explain this tension, right? We should look into the biases, and in our case, we're looking for biases in the supernova side. And yeah, what we have found so far is that we see that there's no dependence on the environment for the color law, which is good. It means that we are ruling out some biases here, some probable causes of the Hubble tension, and also means that probably our understanding of how Taiwanese supernovae work is not so. It's not incorrect. We're going in the correct direction, which is good. Yeah, that's it. Thank you.
Thank you, Tomás, for the very nice talk. So for questions, maybe we reserve the first question to PhD students and young people in general, if there is any, maybe to foster a bit more interaction with the young people.
Junior.
Well, it was a suggestion, but yeah.
So thanks for the talk, Thomas. Can you go back to the tangent with the distribution of the supernova?
Yeah.
So I was wondering, why is that you don't observe that many supernovae in a given interval, like 0.01? Why is it that you have those two and not so many in the middle?
Yeah, that's a good question. I actually don't know. Maybe Luis might know. I don't really know why.
Volume. So look at the completeness is of the surveys are at the peak of the distribution. So the blue distribution that you see there at low redshift is because ZPF or fan stars do not reach depths supernovae peak at 35.2 or something. And those other distributions on the right are small fields, very deep. So certain redshift you will have the area that we covered at 3.4. There are no layers.
Can you maybe repeat?
So it's
the question and the answer.
Yeah. So the question is like, why do we see a gap in this distribution between like low redshift and high redshift? And essentially, this is just an observational bias.
Volume that you survey.
Right. Volume of the surveys. Okay. Yeah. So yeah.
Questions? Was none of us taken from yeah.
Yes, not a young student.
Not really.
I'm very young.
Yeah.
Not that much.
Yeah.
Yes,
Yeah.
So, thank you very much for really very interesting. I have a question. Can you show again the part where you showed somehow this bias that you might have depending on the fact that you might extract the whole galaxies instead of really the region where you had a very nice plot with
This one?
Yes, this one. So my question is, maybe you said, and maybe you did it but didn't say. So if you assume, I guess you might assume how much flux you actually can calculate it, right? Depending on the limit of your images, how much flux in the diffuse emission you're losing in your last as a function of redshift, right? Assuming a certain distribution, let's say the one that you're seeing at low redshift. If you do this, which is the systematics that you would have because of this problem in your H0 error?
Very
Just
good.
to have an idea if this can really be a problem or the systematic related to this would be too small to actually explain that.
Yeah, that's actually a good
Okay,
question.
Tomás, can you repeat?
Yeah, so what Nanda is asking is that, as we go to higher redshift, we sort of can use a model to estimate how much flux we are losing. But like if we do this, how this affects the uncertainties or the biases on the H naught. That was the question, right? Yeah, so that's a very good question. So yeah, so this is actually not my work. That's from Lisa Kelsey in the UK in the ICG. Yeah, I guess so. I haven't done this. I guess you can probably estimate how much flux you are missing, but then you could be introducing biases because then you are, when you're at a really high redshift, it's hard to distinguish what sort of galaxy it is, and sometimes, for example, it is edge on or things like that. So I don't know how feasible that is, and it might be better doing it or not. I don't really know. So yeah, and how precisely would affect the H naught tension? Well, yeah, I don't realize it's actually interesting. I haven't worked much on that yet. I've like recently started working on this.
The high redshift does not affect the H naught tension, as you mentioned. These are all low redshift.
Yeah, but I mean, but you don't need to go to really high redshift to like start losing flux, right? But yeah.
Constantinos?
Thank you very much for the talk. Actually, I was interested in this slide because I don't really understand what is the motivation for looking at the local mass around the region of the supernova. The total mass of the galaxy carries some information about the start motion history and the metallistic history of the galaxy.
Yeah.
And this propagates to the progenitors of the star. However, the local, if you take a random galaxy, you take a random region, you will have the same thing. It doesn't have to be different for a supernova event. Maybe have some difference because you would expect more supernova type 1a stars out there at the radius. But I don't really understand the physics behind the looking at the local property.
Well, that's essentially because you are looking to like if you can actually go to like really nearby galaxy, you can actually see, let's say, for example, the stars, like all the neighboring stars, and you can see that they might be different depending on the region. So if you have a spiral galaxy, for example, the stars in one arm, they might not be the same in the, let's say, in between arms.
Yeah, I understand that. However, what I'm saying is that if you have a supernova event in a binary, the fact that you had another star next to it, not going to affect anything. However, the total mass of the galaxy depends on the chemical evolution of the galaxy. I mean, it's correlated with the chemical evolution. So the chemical imbalances where you made the stars might change the structure of the white dwarf, it might change, let's say, the absorption that you may have around.
Mm-hmm.
So that's what I'm saying. That I understand with the point that you're looking at the environment. However, I think that by looking at the environment, this is my intuition, you're losing information rather than you going in more detail. But anyway, maybe we can, since it's not your, I mean, we can look at this, but I don't really understand why there should be any more information. I mean, you were looking at metallicity, I guess. Now.
Yeah, we can discuss that later. But I mean, at least, we know that if you go into local properties, you do get tighter correlations than going with global properties. That's what I can say for now, at least.
Okay, that's it. Thank you.
Okay. Yeah.
Can you go to the other slide where you are showing the same kind of plot? So the local mass versus the global mass.
Which one I show at the end?
Yes. That's maybe very simple question, but so I understand that all the dots should be below the diagonal line, but there are some galaxies that are above the line. Why is this happening?
That's a good question. I did this plot some time ago. No, it could be, I don't know, maybe the photometry was wrong for some reason, or it could be just that okay. So also like these estimates are using only optical data. So if you want to constrain things like mass, you also need measurements, I believe, in the UV thing. And also it's also useful to have in the infrared to have a more accurate estimate. So it might be just like some random thing or some artifact here. But yeah, I wouldn't be able to tell you like why exactly these are on top. But yeah, I agree that they should be done there. So it might be something artificial.
You have shown that there are several subtypes of the supernovae, and the difference in magnitude and maximum is rather high. So the question is, I wonder, is how will you eliminate the bias introduced by these subtypes?
Yeah, so that's a good question. So yeah, so we have subtypes of Taiwanese supernovae, and how do we remove them in order to, let's say, to have our cosmological sample or cosmological useful sample? That's the question, right? So how do we only get the normal Taiwanese supernovae, right?
Yeah, but in the case of high-energy supernovae, you need to know the spectrum, and so it can contaminate the faraway supernovae.
Yeah, so yes, so most analysis nowadays, we do have a spectrum of a Taiwanese supernova, so we can confirm that it's a first of all a Taiwanese supernova, and it's also not a peculiar type. And then we apply several cuts. So we have a cut in color, right? So we apply a cut in color, also a cut in stretch. So at least going back to the beginning, you can see here, where is it? Yeah. So you can see here, for example, if you apply some cut in stretch, you can, or in magnitude, you can start removing these, let's say, abnormal Taiwanese supernovae, but also apply cuts in color and other parameters. Yes, so we work only with the well-behaved Taiwanese supernovae. In the case in the future, for example, with LSST, now this is you're gonna get a spectrum for every single supernova. So there are some classifiers that work only with photometry. Like applying some machine learning, they work with the photometry and they can classify if something is a Taiwanese supernova or not. Of course, you can have lots of contamination, but there's a lot of work going on in there. But in these cases, mostly just with the spectrum, you can see if it is a normal Taiwanese supernova, and then you apply some cuts in color and stretch and so on.
Okay, thank you. Time for last question, if any. Yeah, then we go.
When you were showing the tool, the
Hotspot, yeah.
that you were removing stars.
Mhm.
So I have two questions to you. One is, how do you identify the stars? So is this done automatically, or you go to some catalogs? And the other part of the question is, so if I get to the masked image, I can still see some residual in the places where the stars were removed. So could this be improved, or what's the plan?
Yeah, so that's a good question. So the question was, we have we apply some masks. So first, how do we identify the targets to remove, and then you have some residuals in the mask image. So can this be improved? Yeah. So the first question here, so Hotspot uses it's called SEP, which is a Python implementation of Sextractor. So with that, you identify all the targets.
So any compact object. So it doesn't matter.
So it can be like anything. Yeah, you give some threshold, some values, and identify targets, and then you have the option to do some cross matching with catalogs. So in this case, I didn't say. For example, you can identify these things here, but they are part of the galaxy, and we don't want to remove those. So you can do some cross matching if you want. Of course, it's not perfect. It doesn't always work perfect. Sometimes it doesn't identify some stars, or it identifies these things. And yeah, maybe in this thing, it looks some of this masking doesn't look quite good. So again, you can also like change parameters, so you make the, let's say, this sort of apertures bigger. So you can do some parameter tweaking as sort of like do it manually sometimes. So yeah, it's tricky, but there's no like automated way of doing it. And you have hundreds of galaxy. It's not so simple. Yeah, you might easily identify these things here, but because you are replacing with one, so this is applying some Gaussian kernel, so it's sort of smooth. So you can, so it doesn't look like noise. So maybe that's also why you can clearly see it by eye. But yeah, I mean, let's say that's maybe it can be improved. It's open source, so you're welcome to check it out and suggest some improvement or things.
Thank you.
Okay, thank you, Tomás, again for all the talk and answers, and let's go for pizza.